in. Okay. All right, there you go, Deborah.
Okay. And by the way, feel free to pop questions in the chat or speak up, or use the reaction icons if you think I'm going too slow or too fast. Okay. So very briefly, um, Mars is the fourth rock from the sun. It's small, cold, and dry. It's about half Earth's diameter, which gives it much less volume. And that essentially plays a key role in why Mars is the way it is now. It turns out that if you want to be a habitable planet, size matters. Um, the habitable zone has gone through several redefinitions over time. So whether or not Mars is in the habitable zone sort of depends on which flavor of the habitable zone you think is the right answer. It's almost certainly the case that Mars would still have a habitable environment today if it were larger, but not forever. Um, it's got lots of geography going on. I am an astronomer, not a planetary scientist, so I have a relatively high level, so to speak, view of that. Um, it has little atmosphere and little magnetic field, and those things are closely related to one another. And Mars is, in fact, red because the oxygen that was once in the surface water bound with the iron in the crust, so it's almost literally rusty. And I still remember one of the early Curiosity drill holes was an area that shows how thin that oxide layer is in some places. And that kind of blew my mind for a long time. Um, so this is a little bit of an eye chart, unfortunately. There's almost no way to get this chart at a good size, but it showed all of the yellow blotches, basically the big picture, are the landing zones for the various Mars missions. So Curiosity is here and Perseverance is over here. This is Jezero crater, which for some reason I have a hard time pronouncing. And this is a topographical map of Mars. Most of you have probably seen one before. It's not quite the whole globe, but it's a significant fraction of it. Some of the more interesting large scale features are that the whole northern hemisphere is lower in elevation. So the blue is low elevation, and then sort of green to yellow to red to white is going up in elevation. This actually doesn't seem to have a key on it, this version. So the areas that are blue, that really means low elevation, but in fact, the fact that that looks a little bit like areas that held water, they probably did. And the crust is thinner as well under these low areas up in the ocean, which is not dissimilar to Earth. There are actually current ice caps also. Those are kind of off the map for the most part. I'm looking in the chat, sorry. Yeah, so Maven, I actually get some mention here. So some of the other key features just for big picture are large volcanoes. Tarsus Ridge here, Tarsus Rise here is a very large volcanic feature that's on an upwelling that's huge. The Valles Marineris is a very long trench. It would basically stretch from New York to Los Angeles. Olympus Mons is the largest volcano in the system. This is a very large impact crater and so on. But Perseverance is running around in this area here. What we haven't done a lot of is being in the ocean areas. This is Viking. That was a long time ago. So Curiosity was the last big rover mission. Its mission was to study whether or not, to try and determine the habitability of Mars. Not specifically to look for biosignatures, but to determine if the conditions had been correct for Mars to have been habitable in the past? And the answer to that is pretty clearly yes. There's an abundance of evidence that there was an abundance of water, both fresh and salt, so lakes and oceans. There are sedimentary rock features. As far as I know, this is the only place other than Earth that we have seen that. There are alluvial fans, which Death Valley is full of because it was underwater once. There's still some subsurface ice presently. It had the right chemistry. That's also a curiosity result. And MAVEN has established that there's a high probability that there was a much thicker atmosphere in the past, and that was, as we have believed for a long time, basically sandblasted away by the solar wind because the magnetic field was no longer strong enough to protect the atmosphere from the sandblasting. So some of them were interesting. This is Olympus Mons here. I think you can see my cursor. Some of them more interesting mysteries that are still floating around. I mean, there are plenty, but these are the ones that kind of speak to me. There's these recurrent slope lineae, which are seasonal stripes on some of the ridges. It was originally thought that they were probably liquid water that was transient. I think there's now an ongoing debate whether it's liquid or sand, but it is some kind of seasonal recurring feature and it's still not well understood. And there are recurring methane plumes as well, which methane biology on Earth definitely produces methane. I think we were talking about herrings not too long ago. On the other hand, there are strictly non-biological processes that can also produce methane. So there's no smoking gun, so to speak, there, but it is interesting that there are recurring, essentially ventings of methane. Process is not known. We just know that Curiosity has detected methane on several different occasions, changing substantially in the quantity over time. So Perseverance is out after the big question. It's looking for biosignatures. And the really big question is, are we alone and who's out there and how many of them are there? So this is the Drake equation. The Drake equation calculates the number of potentially contactable civilizations in the universe. It is a long string of terms, the first one of which is a rate, the last one of which is a time, and the rest of which are just fractions. So you get out of it a pure number. And just briefly, the first term is how frequently you make stars that are suitable for having habitable planets. Second term is what fraction of those stars actually have any planets at all. The third term is how many of the stars that have planets have Earth-like planets. This one is how many of those actually develop life. And then how often is that life intelligent? How often is that life that's intelligent technological? And how long do those technological civilizations last? The point of putting this in a Mars talk is, well, two things. One is, when I was an undergraduate, the only term that we knew was the first one. That was the only one for which we had any quantitative hard evidence to point at. We're now pretty good with the second one, and we're getting some traction on the third one. And we have no earthly or unearthly idea what to do with the third one. If it's zero or very close to zero, Earth may be the only place that has life. If it's large, life may be plentiful. And if it's large and Mars had all the right conditions, that would imply that we should find some evidence of life having existed on Mars. There's no real intent at this point to look for current life. The intent is to look for evidence of past life, but Mars was habitable in the past. So if life is easy to create, then there's a good chance we should find something. So this is a key piece of Perseverance's mission. So that's the background. This is the story of the Mars 2020 and Perseverance rover mission. Checking time here. So this is part of the current set of things that are studying Mars. This is the NASA-centric set. MAVEN is studying the atmosphere. MRO is a mapper. Actually, Odyssey, I think, is a VISA program. And Curiosity is still active, and Perseverance is the new kid on the block with the big shiny wheels. Project like this takes a lot of people. So it was the team in 2019 at JPL posing in front of a building. Sorry, Ellie. We're JPL-ish today. This is just to give you a sense of the size of crew that it takes to make something like this go. When you see the launch on TV, there's a lot of people in that room, but that's just the tip of the iceberg. So and then the other thing is, if you're interested in working on something like this, it takes a lot of people. There are a lot of jobs that you can go out and do and have an impact on a project like this. I got it in my head that, a lot of this was going on, playing out against the background of the pandemic. So I decided to sketch out a little timeline. I found it was kind of interesting. So back in 2016, before we had any idea we were going to be in this boat, the project reached what's called KDPC, or Key Decision Point C. That's basically when a project is well enough along that it gets reviewed by various people, and they say, okay, you can go ahead and start cutting metal. You can go ahead and start making it real. In January of 2020, we went rapidly from realizing there was some kind of weird pneumonia in Wuhan to having a global state of emergency declared. And 1 month later, Perseverance was on its way from JPL to Kennedy Space Center to get integrated with the spacecraft and launched. That was the same month that air travel started to get restricted, and the virus got a name. In March, the virus became an official pandemic, and the stay-at-home orders started, and the rover was being integrated into the spacecraft and tested out at the launch pad. In July, at the time of the launch, the WHO finally said, yeah, masks are a thing. They were a little slow with that. In September, we started to get the new strains, and Perseverance was about a third of the way to Mars. In December, it was still cruising when the first vaccines started to roll out. In February, it landed, and that's when we hit 500,000 deaths in the US. So the primary mission runs from 2021 now through December of 2022, and it will almost certainly have an extended mission unless something goes drastically wrong. But that's the primary mission. That's 1 Martian year. It'll go from where it is currently to the rim of the crater, and hopefully we will be traversing to normality. So the fact that it got named Perseverance is really kind of striking when you look at it this way. And okay, there's a bunch of stuff in the chat. Let me take a quick look. Yeah. Yep. Okay, so how did we get to Mars? I think it's interesting to just look at the visual. When you're doing this, it's always a moving target. So at launch, here's the sun, here's the Earth, here's Mars. As that several months played out, the Earth made its way around to here, Mars made its way around to here, and Perseverance, Mars 2020, had to make its way around to here. So the dots on here are just points at which they did corrections. I'm looking at the chat, sorry. Right, yeah, there's a whole lot of complication to all of this happening against that background. Okay, so I'm going to go ahead and run a short video about the landing. I think most of you have probably seen this. This is the high definition version in case you haven't seen that. At least it's got the high def.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Yeah, I don't think they're pointing the camera, Bill. It's going along with whatever is the motion of the substrate. So not only is it terrifying to land something, which I've also never had to do, but Mars is particularly terrifying to land on. This time, they were all very mellow about all of the different steps that they went through to land it. But when Curiosity is the same strategy, there was a lot more drama around it because, I mean, NASA basically doesn't like to have moving parts, but Mars has just enough atmosphere to be a problem and not enough atmosphere to be helpful if you're trying to land on it. So it takes a lot of different pieces of equipment to actually stop you from burning up and then give you enough ability to slow down that you can make a controlled landing. That's why the first few rovers were basically on big airbags, and we didn't care where they landed as long as they survived. So all of this controlled stuff to get it down there is a huge deal. Okay. Does anybody have questions about that? There's a lot of good information in the chat. Okay, and then I thought this was also another pretty good clip that just explains what the landing site and what the path of the rover is. So it's another short clip.
This flyover was produced from NASA images taken from orbit. The blue circle indicates the area the rover will likely land. The arcing hills in the center, about 1,600 feet high and are the rim of Jezero crater. The central goal of Mars 2020 is to learn whether life ever existed on Mars. It's too cold and dry for life to exist on the Martian surface today. But after Jezero crater formed billions of years ago, water filled it to form a deep lake, about the same size as Lake Tahoe. Eventually, as Mars climate changed, Lake Jezero dried up and surface water disappeared from the planet. An ancient lake is a fantastic place to pursue our goal of looking for possible Martian life. On Earth, lakes are filled with living creatures. Evidence of that life is often preserved in the mud and sand deposited on the bottom of the lake. So, we use the rover's instruments to explore the rocks of the ancient lake bed. Here we can see evidence of the former lake. The canyon cutting through the crater rim was carved by a river. As the water entered the lake, it slowed and dropped the sand and mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years, called the prime mission. During this period, we use the rover science instruments to analyze the lake sediments. After we explore the delta, we hope to investigate the shoreline of the former lake. To get there, we have to traverse around a sea of modern sand dunes. From this perspective, you can see former shorelines curving around a headland. We can picture waves in Lake Jezero beating on a sandy beach. And finally, we will press on to the crater rim. Jezero crater formed when a large object collided with Mars, excavating rocks from deep in the Martian crust, exposing them in the rim for us to study. These rocks would have been hot shortly after the impact and may have hosted hot springs. Deposits from these springs would be another target in our search for possible ancient life on Mars.
Okay, and I just wanted to show you this map. Hopefully this will work. I'm gonna So this is a real-time updating map of where we are that you can zoom in on, whoops, and make everybody dizzy. So it's kind of fun to show where it's been. So hasn't been too far. And then one thing to point out is the scale here is this is 50 meters. And Perseverance is relatively rapid compared to some of the previous rovers. So we can tend to think about the rovers driving around and covering a large area on Mars. That's not true. With Curiosity, I think it was about a year into the mission, they held a 5K at JPL because the rover had covered 5K in a year. So I just wanted to show you this to play around with. All right. So the science mission for Mars 2020 and the Perseverance rover has 4 main objectives. One is to study the geology. That's not my department. I'm sure there are people here who know really a lot about the details of what kinds of similarities and differences we're looking at in detail. Astrobiology, here Perseverance is examining very specific sites and specific rock formations to understand, was there liquid water here? Were there suitable building blocks here? How good is this type of material at preserving signatures of life? And then to select samples for caching. So the big difference here is that Perseverance has the ability to collect and preserve samples that can be retrieved later, brought back to Earth, and studied here. It's not, in most of the areas where it's easy for something like a rover to do an assessment from a distance, the conditions are such that any biosignatures that were there may well have been destroyed by processes going on. The radiation environment on Mars is pretty harsh because there's no atmosphere to filter the UV and gamma and X-ray emission from the sun. So here it can identify areas that have good potential, retrieve those samples and save them. So the sample caching itself is the third goal, and it will collect about 30 samples over the course of the primary mission. And then the fourth goal is preparing to send humans to do stuff. And there are some test technologies there. The helicopter is part of that. And there's another thing that I'm going to talk about in a second. Yeah, I mean, that's, Bill, that's certainly something that could be done, at least to lay some groundwork. I would think we would want to do some automated groundwork laying before trying to send people there for any length of time. But I've never been close to the manned part of NASA. Okay, so we're still really quite early in the mission. So what I'm gonna do for the last little bit of this is walk through the instruments, the science instruments, and show you where I was able to find early sort of commissioning. I mean, it's really in a commissioning phase now, just checking things out and make sure they work. Show what we've got. So here's basically the layout of the science instruments on the rover. It's very similar in overall appearance to Curiosity. It's got some movable instrumentation. It's got some stuff that's more or less fixed on the body. I think everybody would like one. It's really funny because the very first rover was basically kind of a throwaway idea, right? I mean, that was a technology demonstrator. They were just testing the airbag. They didn't really expect to do anything with it. And it was so popular. Everybody wanted to adopt it. I think that was kind of eye-opening. So Mastcam Z, that's this guy here. This is very similar to the camera on Curiosity that, did the selfie work. It's a high definition visible light camera. It's got a very strong zoom on it, and it can also take stereo images. And the motion of the arm is such that it can do 360 degrees around this way and 180 degrees around the other way. So it can basically completely image the environment around the rover. And it's mostly there from a scientific standpoint to look closely at the characteristics of the rock from a distance so that it doesn't have to amble over to every feature to check it out to decide what's interesting and what isn't. And it's looking basically for large scale characteristics of rocks and sand and stuff, like texture, structure, and morphology to decide, is that an interesting place or not? So this was an image from the 22nd of February of the delta from the landing site. This marker shows 10 meters in size. And so this is a very detailed image of Mars. And I'm always struck by how familiar it looks. I mean, it's alien, but it's also really familiar. Of course, I lived in the high desert in California, so what's familiar to me might not be as familiar to some of you. But yeah, I mean, it's pretty cool. Okay, so SuperCam is also an imager, but it has spectroscopic capabilities. And in astronomy, the imagers get all the press and the spectroscopes do most of the science in terms of understanding what things are made out of and what kind of physical state they're in. This has several things kind of bundled together. It also has a laser it can use. Basically, in this case, the laser is to essentially vaporize material so that the spectroscopes can look at it in a more diffuse state. And it collects images to support that, and also because they're good for publicity. And it's also what can be used to capture audio and record it. So I've got a couple samples of sound from Mars. So this is actually the first acoustic recording of the wind. The arrow is sort of pointing at the wrong thing. I don't know why. Okay, so it's wind, but that's the first time human ears, to the best of my knowledge, have heard sound from the surface of Mars that was recorded just the way we would hear it. And here's the little laser zapping a rock called, and I'm not really quite sure how to pronounce this. I think it's Maz. It is the Navajo word for Mars. Okay, so this is the Mastcam Z image of Maz. This is it. And this is a close-up view from the camera on SuperCam. So this is where the laser was aiming at. Don't have the results from that spectroscopy yet because it's still really early. So RIMFAX is, and you start to see how hard we work to get these acronyms to work. RIMFAX means Radar Imager for Mars Subsurface Experiment. FAEX, I didn't even get all the capitals in there. It's a ground penetrating radar. The basic idea here is to characterize in the same location where we're looking at stuff on the surface and trying to understand the content and collecting samples, what the structure is like under the ground down to about 10 meters. And I did not find any data yet from RIMFAX. MEDA, Mars Environmental Dynamics Analyzer. Anthony and Dan, this one's up your alley. This is studying weather and the dust properties. So it's measuring the attenuation from the dust, how much it's obscuring the light. And it's also measuring the wind speed and direction, the wind pressure, I believe, relative humidity, air temperature, ground temperature, and it's looking at the atmospheric properties in ultraviolet, visible, and infrared parts of the spectrum, but not across the whole range in little pieces that are of interest, particular interest. I didn't actually retrieve what those bands are. Pixel, planetary instrument for X-ray lithochemistry. It's an X-ray fluorescence spectrometer and microscopic imager. So it is looking for fluorescence in the X-ray part of the spectrum from rocks that it illuminates with X-rays. So it basically shines X-rays on the rock, and then it takes the spectrum of how the rock responds to that. It also does imaging at a microscopic scale of the area that's I'm looking at. Sherlock, that should say scanning. You can tell I got in a hurry. The name is Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. That's not construed at all. That's a perfectly natural name. This uses a UV laser to do sort of the same thing. It's illuminating the light with a UV laser and then taking spectra of the way the mineral responds to the illumination and takes small scale imagery of the area as well. So those two instruments are very similar. It's just that one is operating in X-rays and the other is operating in ultraviolet light. So they get slightly different science and they need slightly different engineering, but they're basically very similar. And then MOXIE, Mars Oxygen ISRU, In Situ Resource Utilization Experiment. This is one of the main, this is probably the biggest of the studying for potential human presence technology demonstrators. It is going to try to extract oxygen in significant amounts from the carbon dioxide atmosphere, the very thin carbon dioxide atmosphere. I don't think it's started its commissioning yet, so there wasn't anything available to retrieve on what it's doing. But the idea here is both to be able to produce a sustainable supply of oxygen for breathing and also for propellants. And then the last slide is just Perseverance's wheeling on the surface of Mars. It's pretty amazing. It's all new and shiny, right? It's not going to stay new and shiny very long. All right, that's all I have. I'm going to